Hi, I'm Carl Friedrichs, a professor at the Virginia Institute of Marine Science and also the research coordinator at the Chesapeake Bay near in Virginia. The title of my poster, which is actually a 5-slide mini talk, is Controls on Multiple Measures of Water Clarity in the York River. My 6-word story is Clarity Can Suffer from Murky Measurement. A main point of this presentation is that different common techniques for determining water clarity measure quite different things. So whether water is found to have good or poor water clarity depends in large part on how you measure it. I'm presenting some results from Kelsey Fall's dissertation. Kelsey recently completed her PhD working with me at VIMS and is now a researcher at the U.S. Army Corps of Engineers. Between 2014 and 2016, Kelsey led numerous cruises along the York River Estuary. Kelsey compared the controls on number 1, light attenuation, measured by a LightCore underwater light sensor. Number 2, light transparency, measured by a Secchi disk. And number 3, light scattering, measured by a turbidity sensor on an XO2 water quality sonde. The associated water column profiler shown in photo 3 also included a PIX particle camera, a LIST laser sizing instrument, ADV current meters, and a pump for water samples. Kelsey used the measurements she collected at the locations shown by the circles on the York River map to develop optical models for light attenuation, transparency, and light scattering. She then used monitoring data from the Chesapeake Bay, Virginia NERR to validate her models. I will now give you some background on 3 common measurements of water clarity. Number 1 is attenuation of light as quantified by the diffuse attenuation coefficient, also known as KD. KD is determined by fitting a measured profile of underwater light intensity to an exponential decay curve. The units of KD are 1/meters, and the larger the value of KD, the faster the light attenuates with depth. The Chesapeake Bay program considers about 20% of surface light at depth to be the critical value needed for survival of eelgrass. KD is not sensitive to the direction of the light's path, and KD is the measurement considered most closely related to the photosynthetic needs of submerged aquatic vegetation, or SAV. Measurement number 2 is water transparency as determined by Secchi depth, which is the depth at which a 20-centimeter diameter black and white disk is no longer visible to the human eye. To see a sharp image of the Secchi disk, a direct upward beam of light reflected from the disk is required. Thus, Secchi depth, with units of meters, is more sensitive to scattering of light beams relative to the KD measurement. Measurement number 3 is pure light scattering as determined by a turbidity sensor, which is calibrated in terms of nephelometric turbidity units, or NTUs. Typically, turbidity sensors, such as the one compatible with the XO2 sonde, record the fraction of infrared light that is scattered back to the sensor at a 90-degree angle. In this study, Kelsey used optical modeling theory to predict KD, Secchi depth, and turbidity in terms of the total absorption and total scattering coefficients, known as A and B. Total scattering was determined from the LIST laser sizing instrument, and total absorption was then solved using optical relation number 1 for attenuation, knowing KD and B, knowing A, B, and KD. Optical relation 2 for transparency was used to solve for Secchi depth, and optical relation 3 was used to solve for turbidity and NTUs. The final model derivation step is to break down total absorption and total scattering into the contributions due to their individual water column constituents. The absorption due to water and the absorption and scattering due to algae as a function of chlorophyll concentration were taken from the literature. The absorption due to colored dissolved organic matter, or CDOM, was determined directly by Kelsey from her water samples, and the absorption and scattering due to inorganic and organic suspended solids were derived by least squares fits using her measured concentrations of ISS and OSS, each determined via filtering. Together, these equations mean that KD, Secchi depth, and turbidity each can be optically predicted based on water column constituents alone. This slide summarizes the final equations for KD, Secchi depth, and turbidity based on optical theory, and ultimately only as a function of the measured water column constituents of chlorophyll concentration, CDOM absorption, organic solids concentration, and inorganic solids concentration. The three plots display observed versus modeled results for the three measures of water clarity being investigated in the study. Plot number 1 displays KD, plot number 2 displays Secchi depth, and plot number 3 displays turbidity. In each plot, the modeled value for the water clarity measure is on the horizontal axis, and the observed value is on the vertical axis. In each case, the larger open black circles are for measurements made by Kelsey Fall as part of her PhD dissertation, and the smaller filled purple circles are for monitoring data collected by the Chesapeake Bay, Virginia NERR. All data were collected in the York River between 2014 and 2016. For both plot number 1 showing KD and plot number 3 showing turbidity, Kelsey's PhD data were used to determine the best fit coefficients, and the Chesapeake Bay, Virginia NERR data were used for independent validation. For plot 2 showing Secchi depths, the relatively small number of NERR Secchi depth measurements meant that Kelsey's Secchi data were pooled with NERR data plus Chesapeake Bay program data to derive the single adjustable coefficient. The resulting correlation coefficients were between 0.8 and 0.9, and the scatter of data was generally well-centered about the 1-to-1 lines. The equations from the previous slide for KD, Secchi depth, and turbidity allow the relative contributions of the model inputs to be evaluated with respect to water clarity in the York River Estuary. The model inputs are CDOM absorption, the concentrations of inorganic solids, organic solids, and algae, and the absorption by pure water. The three plots on this slide were constructed by binning the observed model inputs according to their associated total suspended solids concentrations, and then inputting the average bin values as a function of sediment concentration. The fraction of the resulting water clarity parameter associated with each constituent is then highlighted in plot number 1 for KD, in plot number 2 for Secchi depth, and in plot number 3 for turbidity. The different colors on each of the squares indicate the relative importance of the model inputs. The relative importance of CDOM is shown in gray, inorganic solids in brown, organic solids in yellow, algae in green, and absorption by pure water in blue. On each plot, a vertical dashed line highlights the case where total suspended solids are equal to 15 milligrams per liter, which is the level that the Chesapeake Bay program has identified as critical to inhibiting eelgrass survival. Even though KD, Secchi depth, and turbidity are all commonly used measures of water clarity, they respond differently to the roles of CDOM, inorganic solids, organic solids, algae, and water itself. For example, when total suspended solids are at 15 milligrams per liter in the York River Estuary, which is about when eelgrass can no longer survive, plot number 1 indicates that only about 1/3 of KD is due to inorganic solids. Instead, KD is more sensitive to the combined impacts of CDOM, organic solids, algae, and the water itself because of their combined contributions to light absorption. At the other extreme, plot number 3 shows that at a TSS of 15 milligrams per liter, inorganic solids are responsible for more than 2/3 of turbidity. This is because turbidity measures only light scattering and does not account for light absorption. The contributions of absorption and scattering to Secchi depth are intermediate to KD and turbidity. Plot number 2 shows that at a TSS of 15 milligrams per liter, inorganic solids contribute to slightly more than 1/2 of the reduced transparency as measured by Secchi depth. In conclusion, KD, Secchi depth, and turbidity measure significantly different aspects of water clarity. Secchi depth, and especially turbidity, are far more sensitive to inorganic solids, that is KD, and KD is more closely related to the light requirements of seagrass. I end by repeating my 6-word story. Clarity can suffer from murky measurement. In other words, whether water is found to have good or poor water clarity can depend on how you measure it. Thank you for listening.